Imagine you were writing like a massive technical manual.
Right, something with hundreds of pages.
Exactly. And you've meticulously coded every single clickable link in your index, right? You've set up this perfect, totally automated pipeline to compile all your raw data into this beautiful, polished PDF.
Sounds like a dream.
It does. Until you hit run, the compiler does its whole thing, and you open that final document only to find that your over-helpful software decided to print all your raw back-end code directly onto the page.
Oh, man.
Yeah, right there for the reader to see. No clickable links, just this massive wall of brackets and hashtags.
That is just soul-crushing for a developer.
Totally. And today's deep dive is exploring a hyper-specific dispatch from the coding trenches that deals with exactly this scenario. We are looking at what happens when two automated systems that are both designed to process data safely try to be, well, a little too helpful to each other.
And they just end up completely derailing the final output.
Exactly.
So we are pulling this from a May 2026 blog post. It's titled Notes on Haskell Programming, Part 140, by an author named Ang.
Part 140.
Right, yeah. And looking at that title alone, you immediately understand this is someone who has been systematically chronicling a very long, highly technical journey
For sure.
through the Haskell programming language. And this specific post, it focuses on a bug that surfaced during a refactoring process for an ebook conversion pipeline.
And look, even if your daily stack doesn't involve Haskell or you've never written a line of it, the mechanics of this bug reveal so much about the friction that happens right at the boundaries where different software systems meet.
It's universally relatable.
It really is. We're going to look at the trade-offs between clean code and processing overhead, the inherent dangers of data sanitization, and honestly, the philosophical limits of automated testing.
Yeah, to really understand how this bug materialized, we first have to look at the architecture of the assembly line that Ang is building.
The pipeline.
Right, the pipeline. The core operation relies on a function called convert to ebook. And this function's main job is just to ingest raw data, which the code calls tokens.
Okay, tokens.
Yeah, and then pipe those tokens through a series of transformations until they finally output as a formatted PDF.
So if we think about this pipeline like a highly mechanized factory, right? You've got raw materials coming in, so those are your tokens.
Yep.
And the pipeline leans heavily on two specific pieces of machinery to process them. The first stage uses a program called Pandoc.
Right.
And Pandoc is basically the middle manager. It maps the raw tokens into an abstract syntax tree, or AST. It parses those tokens and structures them into logical blocks.
Which means it's identifying, what's a header, what's a paragraph, what's a list.
Exactly, organizing the parts. And once that AST is built, the pipeline hands those structured blocks over to a typesetting engine called Typst.
Right, Typst.
Which acts as the final assembly machine. It does the painting and the polishing to give you the final output, the PDF.
The implementation details of how Pandoc handles those blocks in this Haskell environment they're particularly interesting. The source actually notes that the blocks are returned as the fast monoid for content.
The fast monoid. Okay, that term usually gets reduced to that tired analogy of snapping Lego bricks together.
Yeah, the Lego analogy is everywhere.
But in the context of functional programming, and specifically Haskell's architecture, we are really talking about mathematical guarantees regarding processing efficiency.
Absolutely. A better way to visualize a monoid in this pipeline rather than Legos is to think about standardized shipping containers.
Oh, I like that.
Right, because a shipping container is this standardized unit. You can link two containers together, and you still fundamentally have a shipping container structure.
Right, it's just bigger.
Exactly.
Yeah.
You can link 10,000 of them, and the fundamental rules of how they stack and lock together, they don't change. In mathematics, they call this the associative property. It means that whether you combine container A and B first, or B and C first, the final macro structure is identical.
Which is critical for speed, especially in a functional language.
Huge for speed.
Because if the operations are associative, the compiler doesn't have to process the entire document sequentially, from word 1 to word 100,000.
Or it can cheat a little.
Yeah, it can chop the document into chunks, process those chunks in parallel across multiple threads, and then safely merge the resulting blocks together at the end.
Because the monoid laws guarantee the final AST will be perfectly structured.
Right. But why call it the fast monoid?
Well, the fast aspect implies a highly optimized underlying data structure. It's likely utilizing vectors or very strict text types that minimize memory allocation overhead.
Ah, during all that parallel combining.
Exactly. Because Haskell is incredibly strict about types and immutability. Creating and destroying complex tree structures in memory over and over, it can trigger massive garbage collection pauses if you aren't careful.
Right, the system just freezes up to clean house.
Yeah. So relying on a fast monoid for the AST generation ensures the data flows through that Pandoc parsing layer with as little friction as possible.
And that drive to minimize processing friction is exactly what motivated the refactoring that caused the whole bug in the first place.
Naturally. Every good programmer wants their assembly line to run faster.
Exactly. Aang was looking at how the document's index was being generated. The index requires taking specific keywords and mapping them to clickable references in the final ebook.
Which is pretty standard.
It is, but the source explicitly states that their original approach to mapping these tokens and adding the Typst indexing was, quote, quite inefficient.
Yeah, in that initial architecture, the pipeline utilized a totally standalone function named apply Typst indexing.
Okay.
So the data would flow through the token mapping phase to build the standard AST, and then this entirely separate function would have to iterate over the structure again, specifically to inject the indexing logic.
And Aang decided to just delete apply Typst indexing entirely
Just scrapped it.
and folded its logic directly into the initial token mapping phase within a function called token.Pandoc. But wait, I have to push back gently here.
Great.
I always hear that separating tasks into different functions, separation of concerns, is like a core best practice in coding.
It usually is, yeah.
So why is smashing them together into token.Pandoc better here?
It's a good question. Modularity does make code easier to maintain, but it comes with a computational cost. Traversing an abstract syntax tree is not a free operation.
It takes time.
Right.
Yeah.
If you have a document with tens of thousands of nodes running a complete pass to build the base AST and then executing a second distinct pass over that entire massive tree just to find and append index tags, it creates significant processing overhead.
Well, especially considering what you just said about Haskell's immutable data structures.
Exactly.
When you modify an AST in a second pass in Haskell, you aren't just flipping a switch in place.
No, you can't mutate data like that.
You are effectively generating an entirely new version of the tree structure. Doing that twice means allocating memory and triggering garbage collection for an intermediate state that you literally only needed for a millisecond.
Spot on. So by absorbing the indexing logic into tokens.Pandoc, Aang optimized the pipeline into a single-pass operation.
So doing it all at once.
Yeah. As the function reads the raw tokens and constructs the AST nodes for the fast monoid, it simultaneously checks for index keywords and applies the Typst formatting on the fly. It cuts the traversal overhead in half.
That optimization makes perfect sense on a whiteboard, but integrating those steps meant that the middle manager, Pandoc, and the final assembler, Typst, were suddenly forced to interact with the raw string data at the exact same moment.
And it turns out their default behaviors regarding special characters are just entirely incompatible.
When translators collide.
Exactly. We need to look at the exact syntax Typst requires to render an active index link.
What does it look like?
The source provides the exact string. It's hashtag index bracket, keyword close bracket, hashtag link parenthesis, angle bracket index close, angle bracket parenthesis bracket, keyword close bracket.
Wow, okay, a lot of symbols.
Yeah, hashtag index keyword, hashtag link index keyword. Typst relies heavily on those hashtags, the brackets, and the less than and greater than signs to interpret that string as an actionable command.
Rather than just standard text to print.
Right. When Typst sees a hashtag, it switches into code evaluation mode.
Okay, but Pandoc, acting as that AST middle layer, has a very different relationship with special characters.
Oh, very different. Pandoc's primary job is universal document conversion. It takes raw inputs and safely structures them. And to do that safely, Pandoc defaults to escaping special characters.
Escaping them.
Right. If a user writes a technical document that just happens to include a hashtag or, say, an HTML tag as part of a regular sentence, Pandoc cannot risk a downstream renderer interpreting those characters as structural commands.
Oh, because if it did, a stray hashtag could suddenly turn the rest of your document into a level 1 header.
Exactly. Or a stray script tag could introduce a cross-site scripting vulnerability. So Pandoc sanitizes the input.
It plays it safe.
Very safe. It intercepts the hashtag and the less than sign and essentially wraps them in an invisible shield, often by appending a backslash in the raw output.
Telling the system, treat this as a literal, harmless string of ink to be printed, not as executable code. which creates a devastating collision when you integrate it with that single-pass tokens to Pandoc function.
A total mess.
Aang is deliberately trying to inject executable Typst commands into the data stream. But because the indexing logic is now happening inside the Pandoc mapping phase, Pandoc sanitization protocols flag the Typst syntax as potentially dangerous.
And it systematically escapes them.
It's so funny. It's exactly like an overzealous smartphone autocorrect.
Oh, that's a perfect analogy.
Like you type out a complex slang word on purpose, or maybe a Unix command to send to a colleague, and right before you hit send, your messaging app decides the backslashes and brackets are typos.
It fixes it for you.
Right. It automatically rewrites your command into plain English gibberish, ruining the sentence. Pandoc thought it was keeping the text safe, but it actually broke the final product.
Pandoc successfully protected the AST, but in doing so, it completely neutralized Typst's ability to parse the index.
So what happened on the page?
Typst received the escape string, failed to recognize it as a command, and simply rendered the raw, ugly markup directly onto the pages of the final PDF. No links, just text.
So because the automated systems were totally misunderstanding each other, Aang had to find a way to tell Pandoc to back off.
Yeah, the blog post is actually titled Escaping the Pandoc Escape. They had to find a way to override Pandoc's default sanitization specifically for these index links.
Because they couldn't just turn off escaping globally, right?
No, if they did that, the rest of the document would be totally vulnerable to formatting errors.
So it requires this explicit boundary setting.
Exactly. Aang needed a way to signal to Pandoc that a very specific payload of characters should bypass the standard parsing logic.
So how did they do it?
The source details that they resolved the bug by treating the index markup as raw Typst code, utilizing a function called raw_inline.
Raw_inline. Unpack that for us. What does raw_inline actually represent in the context of our factory analogy?
Think of raw_inline as slapping a giant, fragile, do-not-touch sticker on a package.
Okay, I like that.
It explicitly commands the Pandoc middle layer to carry that package, the exact string of characters, straight through the AST generation phase.
But it's forbidden from opening it.
Completely forbidden.
Yeah.
It cannot open it, read it, or sanitize the contents. At a compiler level, raw_inline wraps the string in a specific data type that acts as an opaque pointer.
So when the mapping function iterates over the document and hits a standard text token, it runs its full suite of safety checks.
Right. Standard escaping rules apply.
But when it hits a raw_inline token,
The logic simply copies the byte array directly to the output buffer, completely unmodified.
it forces Pandoc to temporarily suspend its role as a universal translator and act merely as a dumb conduit.
Yes, just pass it along.
So the raw string with all the hashtags and brackets passes completely untouched through the monoid generation, surviving that single pass optimization.
And arriving at the Typst rendering engine with all of its command characters intact and ready to be executed.
It's a highly localized, surgically precise bypass.
It really is. It maintains the massive performance gains of the single-pass architecture without sacrificing the integrity of the downstream typesetting syntax.
Now, the technical mechanics of raw_inline are elegant, but Aang's takeaway from this entire debugging process leads to a final, surprisingly philosophical conclusion.
Yeah, about how we actually validate software.
Right. Aang explicitly notes in the post, and this is key, during the refactoring, I discovered another bug with the conversion during manual testing.
Serial testing.
They go on to state that while they can and do write automated tests to cover this behavior, manual testing remains absolutely necessary.
Which is a bold statement. That pushes against the prevailing dogma in modern software engineering,
For sure. The industry heavily prioritizes comprehensive automated test coverage.
Unit tests, integration tests, end-to-end testing suites just running continuously in the background. Nobody wants to test manually.
But relying solely on an automated testing suite in this specific scenario would likely result in a false positive, wouldn't it?
Oh, absolutely. If Aang wrote a unit test for the tokens to Pandoc function, the test would just assert, given this token, does the function output the correct Typst syntax string?
Right, and because of the new raw_inline bypass, the function would successfully output the string #index keyword.
Yep. The automated unit test would read that string in the output buffer, verify that it matches the expected pattern, and pass with a bright green checkmark.
The continuous integration server reports the pipeline is perfectly healthy.
Everything looks great on paper.
But the automated test only verifies the intent of the code.
Exactly. It confirms the string exists in the intermediate payload. It cannot verify the final physical reality of the rendered product.
Even an end-to-end automated test, theoretically it could open the generated PDF and search the document tree for a hyperlink object, right?
It could try, but even visual regression testing tools struggle heavily with complex typesetting layouts.
Because things shift around.
Yeah, bounding boxes shift based on tiny font rendering algorithms. The boundary, where the digital payload compiles into a visual artifact meant for human consumption, is incredibly fragile.
A machine verifies the presence of data, but a human verifies the experience of the interface.
Well said. Only a human developer, physically opening the PDF, navigating to the index, and attempting to click the link with a mouse, can definitively confirm that Typst actually interpreted the raw inline string correctly.
And painted an active bounding box over the keyword.
Right.
Which really makes you wonder, does this mean our dream of a fully automated, hands-off world is just a myth? When it comes to the final product that humans actually interact with, do we always need a human to act as the ultimate safety net?
I think so. We architect these massive, highly optimized pipelines with fast monoids and single-pass mappings specifically to remove human intervention.
Right, let the machines do the heavy lifting.
Exactly. We want them to handle the data transformation. But this bug serves as a reminder that when the final output is designed for human perception, like reading a book, human intuition is the ultimate non-negotiable safety net.
The machine can confirm it followed the rules, but it requires a human to confirm the rules actually produced the desired reality.
It highlights a really critical distinction between syntactical correctness and functional utility.
Oh, I like that distinction.
Yeah, Pandoc's escaping behavior was syntactically correct according to its internal logic, but it destroyed the functional utility of the ebook.
So to summarize this whole journey, a quest for code efficiency, cutting down those AST traversal passes, led to a clash of systems where Pandoc was basically suffocating Typst's markup in the name of safety.
Over-helpful software.
Right. And resolving it required a hyper-specific bypass, the raw line, which ultimately proved the enduring value of manual human testing. But before we wrap up this deep dive into Ang's pipeline, there is one last, really subtle detail buried in the source code.
Oh, regarding how the keywords are harvested.
Yes. We've spent this whole time discussing how to protect the keywords as they travel through the AST, but the logic dictating which words get indexed relies on an entirely invisible structural layer.
Yeah, the source reveals a very specific extraction mechanism. The pipeline doesn't just scan the visible text of the document looking for important words.
It specifically targets metadata tokens.
Right. The code extracts keywords only when a metadata token, which it designates as tmeta, is present in the stream.
Tmeta.
And conversely, when the function parses the main body blocks of the document, the actual paragraphs and sentences that the user is going to read it, assigns them a value called mempty.
Empty, which relates back to our fast monoid, right?
Exactly.
Yeah.
Mempty is the identity element in our fast monoid. In the context of the keyword extraction pass, returning mempty essentially tells the system, this data is completely empty and irrelevant. Ignore it.
Wow. So the extraction logic deliberately blinds itself to the visible content of the book.
Completely ignores it.
It aggressively filters out the thousands of words forming the actual narrative, treating them as void, and hunts exclusively for the invisible T-meta tags hidden in the document structure.
It just reinforces the concept that the visible output we interact with is entirely subordinate to the invisible structural data defining it.
The physical manifestation of the PDF is literally just a shadow cast by the metadata.
That's a great way to put it.
So the next time you open a polished PDF or you're swiping through a beautifully formatted ebook, take a second to think about the invisible metadata tags hidden just beneath the surface. How much of the structure guiding your reading experience right now is actually just raw code, waiting for the right software and maybe a fragile do not touch sticker to bring it to life?